In this video, I will give an introduction to Approximate Bayesian Computation, or in short, ABC. Let's consider some data D that was generated under a model governed by parameters theta. The goal is now to make inference about those parameters theta from that data. In a Bayesian setting, that amounts to evaluating the posterior distribution, that is, the probability of the parameter vector theta given the observed data. The posterior distribution is calculated as the product of the likelihood times the prior divided by the marginal density or marginal likelihood. The marginal likelihood itself is a normalization constant that is calculated as the integral of the product between likelihood and prior across all parameter vectors. In many applications, this marginal density is really hard to assess. That is, the integral across likelihood and prior does not have an analytical solution. We have previously seen that if, for a model, there is no analytical solution for the marginal likelihood, we can resort to Markov chain Monte Carlo as a method for inference. To run an MCMC chain, there is no need to ever evaluate the marginal likelihood. Today here, we are concerned with a separate problem. That is, models for which the likelihood function itself is intractable. If the likelihood function is intractable, it means we cannot easily calculate its value for a specific parameter vector theta and some specific data d. There are many reasons for why likelihood functions can be intractable. A common case is latent variable models, under which the integral across the latent variable does not have an analytical solution. But for the case here, we are not concerned about the reason for why a likelihood function is intractable. Let's just consider a case under which the likelihood function cannot be easily evaluated. For this case, we now seek an inference method, and we're going to see that Approximate Bayesian Computation, or in short ABC, offers such a possibility. The minimal requirement for Approximate Bayesian Computation methods to work is that we can simulate data D under the specific model. Remember that we use ABC methods for models that have intractable likelihood, so we cannot evaluate the likelihood numerically. However, for most models that have intractable likelihood, it is actually still possible to simulate data under those models. That is, we can draw data vectors D from the likelihood function D given theta for any value of theta. In such a case, we can generate samples from the posterior distribution using a very simple algorithm that is called rejection sampling. Rejection sampling proceeds as follows. In the first step, we sample a candidate parameter vector theta prime from the prior distribution. In the second step, we simulate some data d prime from the likelihood function that is under the model with parameters theta prime. We then accept that candidate vector theta prime if the truly observed data d ops matches the simulated data d prime. We then go back to step 1 and repeat these 3 steps of sampling from the prior distribution, simulating data, and accepting or not for as long as we wish. This algorithm generates samples directly from the posterior distribution. This is easy to see. Parameter vectors are tried according to their prior probability and accepted with a probability that matches that of the likelihood function. Unfortunately, this algorithm is computationally very demanding because it has a very low acceptance rate. That's particularly true if there is a lot of data, in which case the likelihood density or likelihood probability is very, very low. To see this, let's consider a very simple model. A model under which we're going to throw a coin and we can record as data D whether we got a head or a tail. The goal is then to infer the frequency of obtaining a head from a series of heads and tails that we observed from a particular coin. Let's consider a simple case in which the data D consists of a series of a head, a tail, and again a head. Denoting by P the probability that the coin results in a head, the likelihood of this data is then calculated as P times 1 minus P times P, or P at the power of 3 times 1 minus P. Evaluating the likelihood function at P equals 1/2 simply gives us 1/2 at the power of 4, or 1 in 16. Simulating data at P equals 1/2 would thus result in an exact match to the observed data in 1 out of 16 cases. But now let's consider a much longer sequence of data available to estimate P. For instance, let's consider a case in which the coin was actually thrown 100 times. In this case, the probability of a particular sequence evaluated at P equals 1/2 would be 1/2 at the power of 100, which is roughly 7.9 times 10 to the minus 31. That implies that only 1 out of 10 to the power of 31 simulations conducted at p equals 1/2 would actually result in an exact match to our data. Thus, the acceptance rate of a rejection sampling algorithm run for this much data would have an extremely low acceptance rate and be computationally infeasible. And if the data was continuous rather than discrete, an exact match would even be impossible. This is now where approximate Bayesian computation comes in. Let us first look at the most basic ABC algorithm. This algorithm is termed ABC rejection algorithm and is a simple variant of the rejection algorithm introduced on the previous slide. This algorithm proceeds just as the standard rejection algorithm in that we first sample a candidate parameter vector θ' from the prior distribution. Again, we then simulate some data d' under this model, that is, from the likelihood function. In contrast to the standard algorithm, however, we now don't compare that data d' directly to the observed data. Instead, we first calculate some summary statistics S' from that data d'. T here denotes any kind of function that summarizes the data d' in an m-dimensional summary statistics vector S'. The candidate parameter vector θ' is then accepted or not based on a comparison between this summary statistics vector S' with the summary statistics calculated on the observed data. These summary statistics are denoted here by S observed. However, in contrast to the standard rejection algorithm, we don't reject all parameter vectors for which there is not an exact match between S' and S observed. Instead, we accept the candidate parameter vector θ' if the resulting summary statistics S' are close to the observed summary statistics. For this, we calculate a distance between S observed and S', and if that distance is smaller than a threshold delta, we actually accept the candidate vector. We then again repeat those steps for as long as we wish. Before we discuss this algorithm in more detail, let's have a look at the graphical representation of it. On the right here, we see two panels. In the top panel, we see a prior distribution over some parameter θ. In the lower panel, we then see some data generated under this model. Simulations were done as follows. First, a particular parameter θ was drawn from the prior distribution. For this parameter vector, some data was then simulated and summarized as a summary statistics S. Each dot here represents the result of one of those simulations. Let's next compare those simulations against some observed data, or rather, against summary statistics S observed or S-obs calculated on some observed data. Since the summary statistics used here is discrete, there are indeed some simulations that resulted in an exact match with S-obs. However, the number of those is still rather small. Instead of only relying on simulations that resulted in an exact match with S observed, we therefore also accept simulations that resulted in summary statistics close to S-obs. For this, we introduce a threshold delta, and we accept all simulations that resulted in summary statistics for which the distance to S observed is smaller than this delta. These simulations are shown here in blue, and delta is indicated by an arrow on the right. These accepted simulations now constitute samples from an ABC posterior. We can, for instance, draw that posterior distribution using kernel smoothing in the panel above. However, it should be clear that these samples not necessarily come from the true full posterior distribution. An ABC posterior is just an approximation. Specifically, this algorithm generates samples from the following distribution. It's a distribution of the parameter vector given that the resulting summary statistics S are close to S observed as quantified by a distance metric as well as a threshold delta. This distribution reflects the two general approximations almost all ABC algorithms are making. First, we replace the data by some summary statistics. That is, we don't sample from the posterior distribution of the parameter vector given the full data, but the parameter vector given some set of summary statistics. The second approximation is that we can accept simulations that are close to S observed, not requiring an exact match. So we're not sampling from the posterior distribution of the vector of θ given S observed, but of θ given that the S is close to S observed. The reason for making the approximation of working with simulations close to S observed rather than exact matches we have already introduced. it is to improve the acceptance rate of those algorithms. Without such an approximation, the acceptance rate would be computationally infeasible. But let us briefly reflect upon why we actually use summary statistics instead of the full data. There's really two reasons for this. The first one is rather simple. We need to calculate a distance between the data simulated and the data observed. This is rather difficult if we actually do this on the full data, at least under some models. By replacing or summarizing the full data with some summary statistics, it is rather easy to calculate the distance. But there is also a second reason. Namely, the space of the summary statistics is usually much smaller than the space of the full data. Consider again the simple example of throwing a coin with head and tail that we introduced before. We found that if we actually threw the coin 100 times and then we simulated coin throwing, only 1 out of about 10 to the minus 31 of all simulations would result in an exact match between the sequence of heads and tails observed and that simulated under the model. That probability could potentially be much larger if we were to use a clever summary statistics. For instance, if we were to summarize the observed sequence of heads and tails by just the number of heads among the sequence, so for instance, if we had 50 heads out of the 100 times we threw the coin, then the acceptance rate of the algorithm would be much larger because the probability of observing 50 heads out of 100 draws would roughly be 8%, rather than just 1 out of 10 to the 31. And it appears that is something that is very generally true for most models. Summarizing complicated data by cleverly chosen summary statistics may massively improve the acceptance rate of ABC algorithms. Of course, summary statistics have to be chosen in a clever way. One has, for instance, to make sure that they still contain all the information there is in the data regarding the parameters of interest. If you use summary statistics that are not informative about the parameters, then that will of course lead to wrong inference, or rather, to a very broad posterior distribution. Let us therefore reflect about the conditions under which an ABC approximation is actually a good approximation of the full posterior. It turns out that the ABC posterior is a reasonable approximation of the full posterior distribution if two things are fulfilled. First, the chosen summary statistics S are almost sufficient for the data regarding parameter theta. In other words, all the information contained in the data about the parameter vector theta are actually also present in the summary statistics. If the summary statistics are not at least near sufficient for the data, then it means they contain much less information about the parameter vector theta than the full data does. Obviously, this means we will have much less power to infer the parameter vector theta when using those summary statistics than the full data. The second condition to be fulfilled is that the threshold delta is sufficiently small so that the accepted simulations produce summary statistics that are really very close to S observed. If the accepted summary statistics are pretty far away from S observed, then it means, again, that we have a loss of power in our inference. Let us next reflect upon the impact of the threshold delta by using a simple example for which we actually can calculate the true analytical posterior distribution. Specifically, let us infer the allele frequency f from some observed genotypes G observed for some individuals 1 through n. We can assume that the locus here is biallelic with two alleles, an allele A, the ancestral allele, and an allele D, the derived allele. We are now interested in inferring the frequency of the derived allele. We're going to denote the genotypes G by 0, 1, and 2, which actually denotes the number of the derived alleles. So, a genotype equals 0 corresponds to a homozygous ancestral genotype, and a genotype equals 2 corresponds to a homozygous derived genotype. We can further assume that this locus is in Hardy-Weinberg equilibrium, as well as that each observed genotype is independent when conditioned on F. Therefore, the probability of the full vector of genotypes, bold G, given F, is just nothing else but the product across all individuals of the probability of their genotype given F. And the probability of one genotype given F is given by binomial sampling. That is, the probability of observing an ancestral homozygous genotype G0 is given by 1 minus F squared, a heterozygous genotype is 2F 1 minus F, and a homozygous derived genotype occurs with probability F squared. To conduct Bayesian inference, we will further assume that there is a beta prior on the allele frequency f. That is, the probability of f is given by a beta distribution with two parameters, alpha and beta. Under this model, we can actually obtain an analytical solution for the posterior distribution. Given some genotype counts n, that is, a vector of n0, n1, and 2, which respectively denote the number of homozygous ancestral, heterozygous, and homozygous derived allele genotypes that were observed, we get that the posterior distribution of f given a full vector of g is also a beta distribution, where the two parameters are alpha plus n1 plus 2 times n2, and the second parameter being beta plus n1 plus 2n0. Our goal is now to compare how an ABC posterior under this model would actually compare against this analytical solution, and that for different choices of the tolerance delta. Let us first review how we would actually go about implementing an ABC rejection algorithm under this model. Our algorithm proceeds using the classic steps. First, we're going to sample a candidate parameter vector, in this case f prime, from the prior distribution, in this case a beta distribution with parameters alpha and beta. In the second step, we're then going to simulate data given the sampled or candidate parameter vector. In the case here, we're going to simulate a vector of genotypes g prime given the model introduced before. In the third step, we're going to then summarize the full data with the summary statistics. In this case, we're going to summarize our vector g prime with the counts n prime introduced before. That is, we're going to simply count how many homozygous ancestral, heterozygous, and homozygous derived genotypes are within that vector. We're going to then accept the candidate vector f prime using some distance between the observed summary statistics and the simulated summary statistics. Here, we're simply going to use Euclidean norm, d, and we're going to calculate that on the full vector of the three summary statistics. We're then going to accept simulations with distances up to a threshold delta. We're then going to repeat steps 1 through 4 for as long as we wish. Let us next see how well this algorithm performs when comparing it against the analytical posterior distribution introduced before. And we're going to do that under the specific case with observed genotype counts 12, 11, and 2. That is, we have observed 12 homozygous ancestral genotypes, 11 heterozygous genotypes, and 2 derived homozygous genotypes. These genotypes were simulated under the allele frequency f equals 1/3. We're going to further assume a prior distribution with parameters alpha equal beta equals 1/2. Shown here on the lower right are both the prior distribution as a dashed line as well as the posterior distribution as a solid line obtained for that data and under these parameters using the analytical calculations. As we can see, this data is quite informative about the allele frequency. The posterior distribution suggests that the allele frequency is certainly larger than 0.1 and certainly smaller than 0.5, with the most likely allele frequency around 1/3, which was the true allele frequency used in the simulations. So how does now this posterior distribution compare against posterior distributions we obtained with our ABC rejection algorithm? Let us first run the ABC algorithm while setting delta equals 0. That is, we are only accepting exact matches between the simulated and the observed summary statistics vector. In this case, the acceptance rate was only 0.5%. That is, 99.5% of all simulations conducted resulted in a summary statistics vector different from that observed and were rejected. Shown here as a blue line is the posterior distribution obtained from the first 5,000 samples of this algorithm. As you can see, this ABC posterior is actually an excellent approximation of the true posterior distribution. The reason for this is that in this case here, the chosen summary statistics, that is the genotype counts, are actually sufficient for the data. So they contain all the information there is about the allele frequency that is also contained in the full genotype vector. Indeed, under the assumption that genotypes are independent, we don't need to know anything about the order in which those were observed. The reason for why this ABC posterior is not an exact match with the true posterior distribution is simply due to the fact that we use samples in order to generate it. So the posterior distribution shown here was obtained from the first 5,000 accepted samples of this algorithm and then plotted using kernel density smoothing. Of course, by rerunning this algorithm, we might get a slightly different posterior simply because the 5,000 simulations accepted then would not be identical. Let's next see on how ABC posteriors look like if we actually use a delta larger than 0. That is, we also accept simulations that result in summary statistics that don't exactly match those observed, but are just close to it. Shown here as a purple line is an ABC posterior obtained by setting delta to 5. That is, we accepted summary statistics vectors that were distant from the observed summary statistics up to a distance of 5. In this case, the acceptance rate was markedly larger, actually 14%. But the price to pay for this increased acceptance rate is that the resulting posterior is a less good approximation of the true posterior. As you can see, it is a tick broader. That is, we include allele frequencies that are actually considered impossible under the true posterior distribution. Too broad posterior distributions are a standard outcome of ABC algorithms. The reason is that we are accepting allele frequencies for which it's impossible to obtain summary statistics that exactly match those observed. But they may result in summary statistics that are still pretty close to those observed. And this gets just more extreme as we increase the tolerance. In this case, by setting delta equals 10, we have a much broader posterior distribution. Of course, the posterior distribution is still somewhat informative, as it is quite different from the prior and does actually rule out allele frequencies which have very high density under the prior distribution. The benefit of running an ABC algorithm with delta equals 10 in this case is that the acceptance rate is again much higher. In this case it was 32%. And finally here a case with delta setting to 15. Again, the posterior distribution gets much broader, the acceptance rate gets higher, but of course the price we pay is that now the posterior distribution starts to look more and more like the prior distribution. By setting delta to infinity, that is accepting all simulations, the ABC posterior distribution would actually exactly match the prior distribution. So to summarize, by setting delta equals 0, we get an exact match of the true posterior distribution if the summary statistics are sufficient. But even if the summary statistics are sufficient, by using a larger tolerance, we generally get broader posterior distributions. If the tolerance gets very large, the posterior distribution starts to look pretty much like the prior distribution. Note that in case the summary statistics were not sufficient, we would not even get a good approximation of the true posterior in case of setting delta to 0. Indeed, choosing somewhat or at least near sufficient summary statistics is key for any ABC inference. Let us now summarize what we have seen today. I have given you an introduction to Approximate Bayesian Computation, or in short ABC. ABC is a class of simulation-based techniques for Bayesian inference. Because these techniques or methods are simulation-based, they are suitable for models with intractable likelihoods. The reason is simple. We never have to actually evaluate the likelihood function. The only requirement for ABC methods to work is that we can conduct simulations under the specific model. The most basic of all ABC algorithms is an ABC variant of rejection sampling. This ABC rejection sampling algorithm makes use of the two key approximations common to essentially all ABC algorithms. The first one is that we replace the full data with some summary statistics. Using summary statistics instead of the full data allows us to easily calculate distances between simulated and observed data. In addition, the dimensionality of those summary statistics is usually much smaller than the dimensionality of the data. And hence, the acceptance rate of the rejection sampling algorithm is much increased by using summary statistics instead of the data. The second key approximation common to essentially all ABC algorithms is that we accept parameter vectors theta not only if the simulated data matches the full data exactly, but also if the resulting summary statistics are only close to those observed. Accepting simulations with a larger tolerance leads to a much higher acceptance rate of the algorithm. The price to pay for this is that the approximate posterior distribution we obtain gets broader and broader and hence will be less informative. These approximations imply that an ABC posterior is actually just an approximation of the true posterior distribution. However, ABC posterior distributions do converge to the true posterior distribution if, first, the summary statistics S are actually chosen such as that they are sufficient for the data. Hence, they contain as much information about the parameter as the full data does. Second, the threshold for accepting simulations delta has to approach 0. While setting delta equals 0 would actually mean that the ABC posterior matches the true posterior distribution exactly, this is usually not feasible in practice. The reason for this is that the acceptance rate of the ABC rejection sampling algorithm is usually essentially 0 if delta is set to 0. This is certainly true if the summary statistics are continuous. Today, I have only introduced to you the most simple of all ABC algorithms, the ABC rejection sampling algorithm. Of course, much more elaborate methods do exist, and they are generally designed to speed up the sampling process. That means they usually allow for a smaller delta without actually blowing up the computational costs. However, usually they are actually quite expensive to validate. And while we don't discuss this here, validation is something crucial to all ABC inferences. The reason is simple. ABC inferences make approximations. And without validation, we don't know to what degree those approximations distort our inference.